Hi, everybody. We're going to get started in just a couple minutes. Yeah. Okay. Everybody hear me okay?
Yep.
All right. Everybody, I'm Chris Britton. I'm going to be your moderator today. Let me just pull up the program. I actually wasn't supposed to be moderating, so I just kind of jumped in here about 2 minutes ago. So I just want to make sure I double check everybody's here and I have all the names correct. Let's see. This is theoretical mathematics and applied modeling, right? Okay, great.
Is there a link for non-students who want to watch? I've had a couple family members who are interested in watching.
So in order to watch live, you would have to be a registered attendant.
Okay.
But these will all be on YouTube probably within a couple of weeks. So they'll be able to check it out.
Okay, perfect. Thank you.
Yep. Okay. All right. It is 10:31, so I think it's a good time to get started. My name is Chris Britton. I'm going to be your moderator today. So I'm going to thank you all for joining us. This is theoretical mathematics and applied modeling. Oops. Can you all still hear me? Sorry. Zoom told me I was being logged out, but I don't think I have been. Okay.
I got the same message, Chris.
Okay.
I'm in now.
Oh, okay. Are you good?
Yes, I think we're good.
1 second. All right. Okay, Daryl, are you moderating this one then?
I am.
Oh, okay. I've got this open in 2 screens. Okay, great. Then I'll leave you to it.
Splendid.
Okay. Sorry about that, everybody.
Thank you.
Yeah, no problem.
All right. Oh, good morning, everyone. How are you?
Good. How are you?
Fine, fine. My name is Daryl Peterkin. I'm NRHC Vice President, and I am your moderator for this session. For those of you who are still wondering where you might be, we are going to be talking about theoretical mathematics and applied modeling this morning. So I am a historian by training, so I am very anxious to learn quite a few things today. So I'm looking to all of you to enlighten. So our rules are pretty simple. We have 3 presenters, and so each of you have about 15 minutes to present, and then we'll open it up to questions from the audience. And so let's just take a moment for each of you to introduce yourselves, and then we will just adhere to the program. Everyone should have the capability to share your screen and your presentation, and so we will proceed from that point. So without further ado, let's just go ahead and get started. From what I have here, just 1 second, just checking my, checking my schedule. From what I have, Cole, you are going to be going first, followed by Maeve and then Michael. Is that what you all have? All right, yep. Splendid. So why don't we just start that each of you can introduce yourselves and then we'll get going.
I can start. My name is Michael Mandulak, and I am a senior computer science student at Salisbury University.
Hi, everyone. My name is Maeve Cantwell. I'm a senior mechanical engineering major with a concentration in acoustics at the University of Hartford.
Hi, everyone. I'm Cole Bromfield. I'm in my second year at FCC as a mathematics major.
Welcome to you all. As I say, I'm looking quite forward to learning quite a bit this morning. So why don't we just go ahead and get started?
Do you want me to just pull it up and share my screen like usual?
Yes, that will be fine, or whatever you're comfortable with. But you should have screen sharing capabilities.
Okay, awesome. Sorry, my computer's just being a little slow right now.
Oh, I
There we go.
completely
Okay.
understand.
Working now. Okay. I do apologize for the delay. There we go. All right, can you all see my screen? Can everyone see
Yes,
it?
yes, we can.
Okay, awesome. Just let me know when you want me to get started.
The floor is yours, sir.
All right. So my name is Cole Bromfield, and I did my project on infinity. So first of all, let me just start off by saying math is amazing. With math, you can calculate the velocity of an object in free fall at any point in time simply by using the initial velocity and gravitational constant. You can calculate the exact chances you'll get the hand you're going for in a game of poker. You can calculate the mass of an object light years away. But with all math can do for you, there's one topic that has stumped some of the most brilliant minds of all time, and that's infinity. So start off with, what is infinity? It's more than just a number. YouTube mathematician named Michael Stevens classifies it as not a number, but a type of number. Because if a quantity is infinite, it's too great to be quantified. That's why the term really big number just is not enough. So the history, the Greeks were actually somewhat afraid of the idea and used it as a pejorative to refer to someone who is chaotic, and that term was apeiron. Aristotle was one of the few exceptions. He did put some time into studying the concept and described two varieties of infinity, potential and actual. Think about a line being drawn in an empty space. If nothing stops the line from being drawn, it could keep going on forever. That's potential infinity. Actual infinity means a quantity that is in its existence infinite. There aren't many examples of this, if any. The most likely example is space, but even that isn't for sure. In the Middle Ages, infinity was mainly used by religious philosophers to talk about the Abrahamic God. Baruch Spinoza, a 17th century Jewish philosopher, actually believed that if God is infinite, then there cannot be anything that isn't God. The whole world and everything in it, according to Spinoza, is God. However, it was in this time that infinity had its first truly practical use in the math world, and that was with the discovery of everyone's favorite thing, calculus. So how exactly did infinity shape calculus? In the late 17th century, mathematicians wanted a way to calculate instantaneous velocity. They realized that the average velocity over an infinitely small length of time would be the same as the instantaneous velocity. So that's where they came up with this formula to represent the infinitely small change in x, the distance, over an infinitely small amount of time. So the f of t is the function of the time distance as a function of time. And this can be simplified to dx over dt, or the infinitely small change in x over the infinitely small change in time, which if we put in a Cartesian graph we have this. I'm sure anyone who's taken even a semester of calculus can recognize this is the notation for a derivative. So now I'm going to prove that infinity is not a single number. And I'm going to do that with limits. So for example, take this function. Pretty straightforward, but say I want to find f of infinity. To do that, we're going to need to use the limit. And this gives us infinity over infinity, which means we need one of my personal favorite rules, L'Hopital's rule. With L'Hopital's rule, we can take any fractional limit and take the derivative of the top and the derivative of the bottom, and that will give us a new function that will have the same limit as the original. So that simplifies to limit of 4 over 1, which is just the limit of 4, and with our knowledge of limit rules, that's just 4. So in this case, infinity divided by itself equals 4, but it could equal anything. Replace the 4 in the original function with a 5, and suddenly the limit becomes 5, meaning that infinity divided by itself would equal 5 in that case. If it can equal anything, then it cannot be a single constant number, because any single number divided by itself famously equals 1. But the craziest thing about infinity is that it actually exists on multiple levels. The one most people are familiar with is the one that can be counted to in theory. But that's just the first level, and it's known as Aleph Null from the Hebrew alphabet. It's also known as countable infinity, although that may be confusing since it would literally take forever to count to. That's why I prefer to call it listable infinity, as the numbers in the set could be placed on a never-ending list. So what would the next level be? Let's try all rational numbers. That is, all numbers that can be expressed as a ratio of 2 whole numbers. So now we're not just looking at integers, we're looking at fractions as well. Before we go over that, I'm going to cover an important principle known as Galileo's paradox. Galileo was an infinity pioneer, and he raised an interesting question. There should be more numbers in existence than numbers that are perfectly square, right? But there are actually the same amount. Galileo postulated that since for every positive integer there is exactly 1 square number, there must be the exact same number of whole numbers and square numbers. Look at this table if it helps. Although logic would dictate that there would be more total numbers than square numbers, you can actually line them up 1 to 1 with each other and do that to infinity. And this is called 1-to-1 correspondence. A set having 1-to-1 correspondence with Aleph Null will have exactly Aleph Null terms in it. So if we can't get 1-to-1 correspondence with Aleph Null and all rational numbers, then that must mean the set of rational numbers is more infinite. So to set this up, say we take the set of 1 over every number from 1 to infinity. Then we do the same with 2, then 3, then 4, and so on. This would appear to be more infinite than Aleph Null. It is infinite not in 1 dimension, but 2. So how would we possibly get 1-to-1 correspondence? Surprisingly, there's a way. Start with the very top left, 1 over 1. Then move to the right and go diagonally. Then repeat. And just keep repeating like that. This set could be listed in a straight line, as you can see, which would give it 1-to-1 correspondence with Aleph Null. So believe it or not, there are the same number of whole numbers as there are fractions. So that probably raises the question in your mind, how could a sequence possibly not be countable? Like, couldn't you just take any set of numbers and put it in 1-to-1 correspondence with Aleph Null? Well, to start off, imagine 10 infinite sequences. The first is Aleph Null, the rest are random. Say we wanted to make a new sequence that was completely unlike the first 10. Maybe we make a sequence whose first number matches the first sequence, second number matches the second sequence, etc. And everything after the 10th number is random. In all likelihood, this would create a new sequence. However, there's a chance it matches one of the first 10. And if you take a look, its first 10 terms do match those of S9, meaning there's a small chance, however minute, that they match all the way to infinity. So this method is not a surefire way of creating a unique sequence. But what if we do the same process, but change each number? Like so. No matter what random numbers come after the first 10 terms, this sequence is at the very least one number off from each of the first 10. This can be repeated forever. Every new sequence will be completely unique. Now, imagine each sequence is a decimal number. The first number is the ones place, and then after that is each decimal place after that. Irrational numbers work the same way. An irrational number such as pi, e, or the square root of 2 has a never-ending series of digits following the decimal place with no rhyme or reason. No matter the length of a list of irrational numbers, a new and unique number can always be created, meaning that this set is not listable. All whole numbers, all square numbers, and all rational numbers, all of those sets had order. They had a specific structure for what comes next, which could go on forever in a list. But this is not the case with irrational numbers, as the next number could be of any relation to the previous, and there is no progression, rhyme, or reason of any kind. So the set of all real numbers, that is both rational and irrational, is more infinite than Aleph null. So it seems we've found our next level. This form of infinity is known as Aleph 1. Now, you're probably wondering, is there an Aleph 2? Perhaps Aleph 2 could be a power set or a list of every possible permutation within a set of Aleph 1, in the same way Aleph 1 is technically a power set of Aleph null. Mathematicians are really divided here. A power set of a number or set will always have an exponentially greater number of terms, but as we've already shown, exponentially greater does not necessarily mean more infinite. It did in the case of Aleph 1 compared to Aleph null, but perhaps the power set of Aleph 1 would still have one-to-one correspondence with Aleph 1, and there's really no way for us to test that. So this is the point of infinity beyond which it has not really been explored. So I'm just going to finish with a couple cool tricks you can do with integration and infinity. So take this function. Let's find the volume and surface area of the function when it's generated in a circle around the x-axis of the solid generated when we do that. So this is the formula for volume of a function. So here's the integration we have to do, and that gives us this, which is equal to this. Looks like the faces are in the way. Let me just move that real quick. Sorry. There we go. So that gives us pi. Pi is the volume of this function as it goes to infinity, and it's rotated around the x-axis. So now let's find the surface area, remembering that the volume equals pi. So here's the formula for surface area, which will set up this integration. And this looks incredibly difficult, painstakingly so. However, there's a trick. For all positive values of x, this new function will always be less than the one on the left, this function right here that I created. The square root of 1 plus 1 over x to the fourth will always be greater than 1. I think we can agree on that. So from here, this is a pretty easy integration. And since the natural log of 1 is 0, that just leaves us with 2 pi times the natural log of a. The limit of this function as a approaches infinity is infinity. So if that function integrates to infinity, then it would certainly follow that an always larger function with the same bounds would also integrate to infinity. Therefore, the surface area of this solid is infinite. But wait, this means this solid has infinite surface area, but finite volume. Hence, it's a paradox known as Gabriel's horn. And it looks like this. Pretty crazy. And just one more cool thing with infinity before I go. Black holes. These are formed when an object such as a collapsing star at the end of its life becomes so dense that much of its mass collapses into a single point known as a singularity. A finite mass contained within an infinitely small volume means infinite density, and this leads to some very weird things happening. Past the event horizon or point of no return of a black hole, even the laws of physics and Euclidean geometry disappear. Distances the way we know them cease to exist. Every object in space, planets, stars, moons, they all have what's called an escape velocity, or a velocity required in order to escape the object's gravity. A black hole's gravitational force is so strong, the escape velocity is greater than the speed of light. This is why black holes appear black, because not even light can escape from them. Just for some perspective on how dense these things are, the sun's entire mass would need to be compressed within a 3-kilometer radius for it to collapse into a black hole. For the Earth, its mass would need to be compressed within a radius of 2.5 centimeters, or about the size of a baseball. And for a human's mass would need to be compressed into an area smaller than the nucleus of an atom for the poor human to turn into a black hole. Point is, black holes are a crazy example of how mind-boggling the infinite can be when it occurs in nature. So just to wrap things up, I know infinity is crazy. It creates paradoxes. It gave us calculus. It creates black holes. It gives us some truly strange mathematical concepts. And if you're having trouble wrapping your head around it all, you're not alone. So with that, I'm just going to leave you guys with a Galileo quote. When we attempt with our finite minds to discuss the infinite, assigning to it those properties which we give to the finite and limited, but this I think is wrong, for we cannot speak of infinite quantities as being the one greater or less than or equal to each other. So Galileo really understood how crazy infinity is and how hard it is for the human mind to grasp. And that's it. Thank you.
Thank you, Cole. And yes, this is just beyond my understanding, but you also did a lot with one of my great historical heroes, Galileo. So I'm looking forward to some questions in the question and answer session. So let's move on to our next presenter.
Let me just share my screen here. Okay, so as I introduced myself before, my name is Maeve Cantwell. I'm a senior at the University of Hartford studying mechanical engineering with a concentration in acoustics. And my presentation is titled Hearing Space, Modeling Concert Halls to Achieve Understanding Through Acoustics. So just before we begin, if you have headphones or earbuds handy, then I recommend you use them. I'm going to be playing some audio files that are in stereo, meaning that they have different sound in the left and right ear. And it's easier to hear these if you have headphones. If you don't, that's fine, don't panic, you'll still be able to hear them. So the purpose of my project was to create 3D computer models of 3 different concert halls and use these models to estimate the acoustic parameters of the spaces. What I was mainly focused on was one acoustic parameter called reverberation time, which is basically the amount of time it takes for a sound to die out in a space. So if you think about reverberation time, it's like if you clapped your hands or popped a balloon in a space, it's then how long it takes for that sound to fade so that you can't hear it anymore. Once I estimated these acoustic parameters, I was able to create realistic auralizations from the models. And an auralization is basically an audio recording, except it's made purely from a computer instead of from a physical space. The 3 concert halls that I looked at in order of increasing reverberation time were the Philadelphia Academy of Music with a reverberation time of 1.2 seconds, the Kennedy Center Opera House with a reverberation time of 1.5 seconds, and the Grosser Tonhalle with a reverberation time of 2.0 seconds. So to create my models, I used a free software called SketchUp. Some of you may have heard of it. If you haven't, it's just an easy to use software that creates surfaces instead of volumes. And I based the volume of the space and the overall structure off of architectural plans and sections from a book by Leo Baranek called Concert Halls and Opera Houses. And this is a comprehensive book of 100 different concert halls and opera houses from all over the world. And not only does it have these architectural plans and sections, it also has acoustic data, which is what I was basing my comparisons on. I then took details such as columns and people, maybe organs from photographs of the different spaces. And then I used a feature in SketchUp called sorting by layers to sort the different surfaces into similar groups. So if you see here in this picture, the organ is an orange, And it is a different type of surface from the walls, which are in blue. So those are on 2 different layers. To set up my models, I imported my SketchUp file into a room acoustic software called Odeon. And then I used the layers that I had created in SketchUp to assign materials to each surface. So for example, the organ is, I made a custom organ material. Well, the stage would be wood and columns were usually marble or another form of stone. I based the material properties off of what they appeared to be in photographs. And then I tweaked the different materials that I had assigned to each layer until the estimated reverberation time given by the Odeon software matched the physical reverberation time of the space as given by the Leo Baranek book. And even small changes in material can cause large changes in reverberation time if there's enough of that material in a space. I then placed sources, or things that create sound, either on or near the stage. So I placed a person talking, which I'll call a talker source, along the central axis of the space on the stage facing forward into the audience. I then placed a trumpet source either at the front of the stage or in the orchestra pit, off to one side a little bit and facing where a conductor would be standing. I also placed receivers, basically ears, throughout the audience section of the space. So these are the different source and receiver locations that I had. The source locations are in blue and the receiver locations are in red. So as you can see, the Academy of Music and the Kennedy Center both have orchestra pits. So that's where I placed the trumpet in those situations. The Grosser Town Hall Saal, though, not being a form of opera house, being purely a concert hall, only has a stage and no orchestra pit. So I placed the trumpet at the front of the stage and the talker source sort of in the middle of the stage. And as you can see, the receiver locations are evenly distributed throughout all the spaces. So now we go on to how I analyze the models. The way Odeon analyzes models to create oralizations is that it first creates something known as an impulse response. And this is basically a very brief audio file that describes how a space reacts to an initial sound put into it. So these files are nothing interesting to listen to. They kind of sound like your ears are popping or something. But the great thing about these files is that you can do a mathematical technique called convolution with an anechoic source file. So that's a lot of big words. Convolution is basically, to use the untechnical term, mushing 2 things together to create something that's greater than the sum of its parts. It's done mathematically with a whole bunch of different sources. So each of these, the impulse response file and the anechoic source file, are sampled with 44,000 sample points per second. So that's a lot of sample points, and each one is being correlated to the one in the other file to create the new oralization file. And an anechoic file is basically a file that has no reverberation at all. It's created in something called an anechoic chamber, which is a completely dead space. So to give you an understanding of the anechoic files that I used, here are the 2 different sources. So here's the talker source.
In 1895, Harvard University had just completed the Folk Art Museum.
And could everybody hear that? If you could just hear that, could you put it in the chat?
Yeah, I heard that.
Okay, thank you. And then here's the trumpet source. So if you notice, these 2 files sound really dead. They almost sound like they're fake. But once you convolve it with the impulse response, it sounds like you're actually in the space where the source and receiver were placed. So now we go on to comparing the sounds of the 2 spaces. So going from lowest reverberation time to highest reverberation time, if you listen to the talker source, you'll notice that the spaces become more and more reverberant, meaning that there's more excess sound energy beyond the person speaking. And so this means that lower reverberation time, the Academy of Music, for example, has a very high intelligibility. It's very easy to understand what the person is saying. Whereas in the Grosser Town Hall Saal, it's fairly intelligible, but it is definitely harder to understand. So I'm just going to go through and play all of them for you so that you can hopefully get an understanding of what I mean. So here's the Academy of Music.
In 1895, Harvard University had just completed the Folk Art Museum.
And now here's the Kennedy Center.
In 1895, Harvard University had just completed the Folk Art Museum.
So if you listen carefully to these two files, you can definitely tell that the Kennedy Center has more reverberant energy around the speaker. So it's a little bit harder to understand what the speaker is saying. Now let's listen to the Grosser Tonhalle.
In 1895, Harvard University had just completed the Folk Art Museum.
So as you can tell, this one is definitely the most reverberant out of all three of the spaces. Now let's move on to the trumpet source. And these ones are a little bit harder to tell the difference between them. But if you go through them in order of lowest reverberation time to highest reverberation time, you'll notice that the Academy of Music has very crisp and clear notes. While in the Grosser Tonhalle, the notes blend a lot and they create a very rich sound. So let's listen to those. Here's the Academy of Music. And the Kennedy Center. And those two files are pretty similar, but now listen to the Grosser Tonhalle. So that one, I think it's pretty clear that the notes are blending a lot and it creates a much more rich sound in the music. So another thing that I wanted to look at was to change the reverberation time of one of the spaces. And the reason I wanted to do this is because there's always a question in the acoustics community of how much of a space, how much of the sound of a space is determined by the reverberation time, and how much of it is determined by the geometry of the space. So to do this, I took the Kennedy Center, which has a reverberation time between the other two concert halls, and I changed the materials in Odeon to change the reverberation time down to 1.2 seconds and up to 2.0 seconds. And then I compared it to the other two concert halls to see how realistic it sounded. So let's listen to the talker source for the lowered reverberation time.
In 1895, Harvard University had just completed the Folk Art Museum.
And now compare that to the Academy of Music.
In 1895, Harvard University had just completed the Folk Art Museum.
So if you're unable to wear headphones, these files might sound exactly the same. But if you are wearing headphones, then you probably noticed that the Kennedy Center still sounded a little bit more reverberant than the Academy of Music did. So let's move on to the trumpet source and listen very, very carefully to this one. And on to the Academy of Music. So these two files do sound very similar, although if you listen to them closely, and if you go back and forth between the files about 20 times like I did, then you'll notice that the Kennedy Center does still sound a little bit more reverberant. The notes are still blending a little bit more. So that seems to indicate that maybe this change in the reverberation time doesn't make much of a difference. But let's go on and see how raising the reverberation time sounds. So here's the talker source for the Kennedy Center.
In 1895, Harvard University had just completed the Folk Art Museum.
And here's the Grosser Tonhalle saw.
In 1895, Harvard University had just completed the Folk Art Museum.
So again, these files sound pretty similar, although if you do listen to them a few times, the Grosser Tonhalle definitely has more reverberant energy just in the background of the file in general. Now let's listen to the trumpet source. And again, listen to these ones very carefully. And now the Grosser Tonhalle. So again, I think that the Grosser Tonhalle seems to have a more blending of the notes, a richer sound. But I have also listened to these files quite a bit. I wish I had more time to share all the files I created with you, but unfortunately we're on a time limit. So you might listen to this presentation and gone, well, Maeve, that's all very interesting, but why did you do it? You know, cool results, but why? So one thing that can really be done for this research is to, pave the way for future research. And something that's actually being done right now by some of my colleagues or peers, I guess, at the University of Hartford, is they're doing what's known as a just noticeable difference study. And this is basically how much can you change something before a person notices that you have made a change. So this is kind of like what I was doing with the Kennedy Center and changing the reverberation time to see if there was a difference. And this is really important because it helps us understand how people perceive sound. And if we can understand how they perceive sound, we can create spaces that appeal to a majority of people. So whether it's a concert hall or even just an office building, everybody has different acoustic preferences. And if we can make spaces that people feel comfortable in, then that's great. That's kind of the goal of acoustics, is to make people feel comfortable and not even notice the sound of the space that they're in. And then another thing, something that I'm personally very interested, is that this research can be used to either preserve or revive historic spaces like concert halls and lecture halls. A lot of these spaces have been modified over time, just as they've aged and needed repairs. But many people are going back now and trying to get them back to their original sound. So if we can create these spaces in SketchUp and import them into Odeon and do the oralizations, we can figure out exactly how every single space in that concert hall or lecture hall used to sound when it was first built. And we can use that when we're preserving these spaces. So that's all I have. I'd like to thank several of my professors at the University of Hartford for helping me out with this project. And again, my name is Maeve Cantwell. If you have any questions that you can't ask during the question and answer period, my email is at the bottom of the slide, just cantwell@hartford.edu. Thank you very much.
Thank you, Maeve. All right, I think, Michael, I believe you're up.
Awesome. 1 second. All right, so my name is Michael Mandulak, and I am a senior computer science student at Salisbury University. And I will be talking to you today about parallel algorithms and the stable marriage problem. 1 second. All right, so to give a quick overview of my presentation, I will kind of lead you through the logical progression of research in terms of first introducing the stable marriage problem and providing some methods for parallel algorithms and how we analyze those for efficiency. So first, the stable marriage problem is a theoretical matching problem proposed in the 1960s by David Gale and Lloyd Shapley. And the problem poses a scenario of two gender-separated sets of men and women. And alongside each of these sets, we give a preference list. So each person ranks the members of the opposite gender based on marital preference. And so the question is, how can we form a stable matching between those two sets, the sets of men and women? And a matching is considered stable if no two people prefer each other over their matching partner. So it'll be no mutual preference and everybody will be conditionally happy with their matching partner. And so alongside this algorithm, David Gale and Lloyd Shapley proposed the Gale-Shapley algorithm, which takes at most a worst case of n squared, which is fairly reasonable for sequential algorithms as we go over the preference lists of each person involved. And eventually in the Gale-Shapley algorithm, each person will propose to their top, or so each man will propose to their top ranked choice and that they have not yet asked. So in the worst case, we will go through everybody's preference list, so taking a quadratic time complexity. But when we look at parallel algorithms, typical parallelization schemes would try and have men propose to multiple women at the same time. But we see that this doesn't work for efficiency's sake, because it is not efficient to consider for women to consider multiple partners and not take more iterations than the sequential Gale-Shapley algorithm. So as you can see in the image, we can model preference lists as a matrix where when we go down the columns, we have the women's preference of that man. And then we go across the rows and we see the man's preference of that woman. So for example, in the top left corner of the matrix, we have man 1 who ranks woman 1 as his highest, being noted by the 1 in the ordered pairing. And man 1 is woman 1's second most preferred choice. And this is kind of the basis of the parallel iterative improvement algorithm, which I will talk about. But to kind of outline the goals of the project, this problem has a lot of applications in general matching scenarios, such as university admissions, dating applications, organ transplants, those things of those nature, where, for example, if you're a university student applying to a school, you will likely create an internal preference list of, I prefer this school over the other for reasons such as academic goals or facilities of things of that nature. Similarly, the university will create some internal list of students they prefer based on academic merits and scholarships, funding, things of that nature. This application also includes in computer networks. When we are distributing information in packets, it is likely that we have routing algorithms to efficiently distribute this information, as well as servers. When you connect to a server, you try and find proximal connection, fast connection. We kind of want to make those things as efficient as possible. So that's why we are looking at using parallel algorithms, which use multiple processing elements to speed up the finding of stable matchings. So first in this research project, I looked at implementation of 2 of the main algorithms, the parallel iterative improvement and the convergent parallel iterative improvement algorithms. So these algorithms function by finding the man's most preferred choice in any matching. So if we go back to this matrix, in this case, we will start with all the 1s in the left position of the ordered pairing, which is kind of a greedy approach of finding the most optimal, the most stable pairings in an iteration, and having those pairings eliminate other pairings. So for example, the pairing in the top left will eliminate the ones in its row because it is the man's most preferred choice. So he has no reason to ask in this iteration any of the other women because he is currently engaged to his top choice. So when implementing these algorithms, using Salisbury University's high performance computing lab, we kind of note the trends. And you can see the parallel iterative improvement algorithm follows a linear trend pretty well, which is expected with the algorithm. But the CPI algorithm didn't have a lot of testing behind it. So we kind of note a logarithmic trend at the start. And then there's this spike at n of 19, which we found very interesting. We assume that this case was because of typically time complexities start at some n0 point. Because when we're looking at the worst case, we want to test it for very large data sets. But given the HPC using all of the resources on the high performance computing lab, we can only test up to n of 20. So we wanted to do some more research into the CPI algorithm. So when we look at the CPI algorithm, we have to ask ourselves, like, what does a worst case input look like? And how long would such an input take to find a stable matching? So using the CPI algorithm, we note that the algorithm focuses on partial matchings. Usual matchings will have size n, so the number of men or women, number of pairings, while in these cases, you'll notice that the dark highlighted squares are the current matching pairings, while the light highlighted squares are stable pairings, and then the white squares are unstable. So we will receive a stable matching when all of the unstable pairings are eliminated. So as you can see in the bottom right on K8, we have 1 pairing left to pick, and it is not interfered with by any other matching pairing. And that's kind of the goal of finding a stable matching. And so throughout this progression, we can see this pattern where as you go from left to right, top to bottom, you'll notice that we kind of repeat over, we pick only 1 pairing, which is the worst case, where we keep adding 1 pairing per iteration. And going off of that, we kind of go back through the algorithm and we replace these pairings to find most optimal pairings. Because ideally, we would like to find multiple pairings in a single iteration, which would be the most efficient. But for the worst case, we see that it follows at most 2n minus 2 plus log n steps, which amounts to a linear time complexity. So noting that, we see the logarithmic trend as well as the spike in the previous results, and then we see a linear trend in these results. So we kind of associate the CPI with a more linear case, which is better than the quadratic case of the sequential algorithm. But we kind of want to see if we can find some more improvements. These are some implementation results that kind of follow that linear trend that I was talking about with a sequential test where we ran 300,000 tests per n. We had a very good linear fit for a sequential coding implementation. And we see those similar spikes. You can see at 49 and 19, we have those spikes towards the upper bound that kind of match the results from the first implementation. So then we look at how can we how can we study these sets further? Now, in the PII algorithm, the reason we don't use the PII algorithm for applications is because it has this cycling issue where because of the greedy choice of pairings, we see that it doesn't always terminate a stable matching, whereas the Gale-Shapley algorithm always terminates a stable matching no matter the input set. So then to look at these input sets further, we use evolutionary algorithms. So an evolutionary algorithm is an algorithm that replicates input sets as a binary input, and then we can perform typical mutations, crossbreeding, and fitness evaluations for those input sets to kind of determine how well they fit a certain data set. So using that, we use a mutation-based evolutionary algorithm. So we model our binary input as a matrix, a lot like the first chart or these charts. You can see we would model all of the dark highlight squares as ones, and every other pair would be a 0. And so using a bit flip method, which is common in evolutionary algorithms, we can modify the matching and swap 2 of the pairings row and column positions and obtain a new input set. And so this, as we optimize further, we can kind of see the placement of pairings as we continue and as we look at a lot of input sets. So these heat maps on the screen, they model how often certain pairings appear in a certain matching set. And so for the n equals 6 one, so the 6x6 matrix, and the n equals 11, the n equals 11 is a cycling case where it does not terminate with the PI algorithm, while the n equals 6 one is. And we can note a few trends in the input set, such as on the n equals 6 one, the very light yellow square is of the pairing 6, 5, which, since we're always trying to minimize the numbers for a more stable pairing, is pretty interesting that it's included the most out of all their pairings, given how unstable it is relative to the entire matrix. And we can see a similar trend in the n equals 11 heat map. We can also note a lot of the lighter squares, or a lot of the dark purple squares, are female optimal cases. So we consider a male optimal case a pairing that is minimized in the left slot of the order pairing, while a female optimal is ordered in the right. So this kind of brings up the idea of matching optimality, where how can we apply this to the algorithm to kind of consider in both cases the men's most preferred and also the women's most preferred, and kind of equalize that. So when we look at the PII-SC algorithm, it's an improvement upon the PI algorithm that still does not fully solve the cycling case, but it has a few cases where it doesn't terminate. We call it like a few special cases, such as 3 in a rows, holes, long cycles, and dead ends. So as you can see in the graph, for example, the one in the top left, the purple node in the matrix is a hole. So the matching returned from the PI-SC algorithm was missing a matching pairing. So it wasn't fully complete. It was partial, like that of the CPI algorithm. And so we try to solve these cases by applying that idea of gender optimality, in that if we notice from the heat maps and from a lot of input study, we can see that a lot of the female cases, a lot of the female optimal pairings are these whole cases, or these 3 in a rows, or these long cycles, or these dead ends. So we try to include that in the algorithm to always terminate with a stable matching. And so for some improvements, we made some changes. We improved the initiation. So initially on the PI algorithm, we start with an arbitrary initial matching, which is really good at preserving that diversity in optimality, where it's equally as likely to be male preferred as female preferred. When in the PI-SC algorithm, we use an initiation phase similar to the Gale-Shapley to improve the success rate of the algorithm. We lose that diversity and we go back to a male optimal or female optimal pairing. But improving upon that, we add in some alternate initiation phases. So typically we run the algorithm with a male optimal, where the men are the ones proposing to the females, while we can also look at input cases where the females propose to the males. And then we can also look at similar cases where we mix up the ordering of the proposers, and we consider pairings that aren't as optimal in that current iteration, which we consider the male log optimal and the female log optimal, to achieve a stable matching very quickly. So in the example case on the matrix, the top matrix is using the male optimal. You can see in the first iteration, we choose a matching that does not remove all of the unstable pairings. But if we run the same matrix with the female optimal, we can find it in a single iteration, and we can eliminate all unstable pairings. So we apply this to the algorithm alongside some limits to the cycle detection phase, which were some basic improvements to the PI algorithm that achieved about a 99% accuracy, but our focus was on closing this one case using the input study we determined earlier on. So in our implementation tests of this algorithm, we found that there were no, in 1 million tests per n for n of 4 to n of 100, we found that there were no non-terminating cases using these improvements. And we retained the linear worst case time complexity, but a few of the issues with this algorithm is that the runtime is significantly increased compared to the original algorithm. So its applicability is slightly removed for the applications in university matching and similar problems. So one of the future works on this is to improve that worst case runtime while also including some gender optimality considerations within the algorithm without such initiation changes. And we also want to do some testing to look at these initiation phases independent of each other, because how we sequence the initiations as listed here, we follow that if the male optimal does not terminate with a stable matching in the algorithm, then we continue with the female optimal and then the male log and etc. We want to look at these initiation phases independently, because we believe that there exists a way to classify certain input sets with a gender optimality to make an efficient stable matching a lot easier to determine. And we want to use machine learning algorithms to do that, which I've currently used evolutionary algorithms, but we do want to look at some kind of neural net way to study these input sets in mass, and to eventually just define the origin of cycling in the PI algorithm, while also making improvements to the algorithm's efficiency and utilizing the CPI algorithm as an efficient way to determine these stable matchings. So that's my presentation. Thank you very much for listening. If you have any inquiries about my work, my email is there, as well as my mentor's email. And thank you so much.
Thank you, Michael. And may I say that maybe it's because all of you are in mathematics, but the precision with which you've adhered to time has been remarkable. So thank you very much. So we can open the floor up to questions. For those of you who have questions, you can certainly put them in the chat. I see that there are a few there already. So why don't we go ahead? And you can also, of course, use the reaction key to raise hands to go ahead. So the floor is open. All right, well, I'll go ahead and ask a question. I am an historian by training, so I apologize at the very beginning. I was intrigued by your discussion of black holes. Could you just give us a little bit more about that? Of course, as a science fiction fan, I know of black holes as sort of a trope used in that genre of literature, but how, and I don't know if you read it as well, but if you do, how closely do they adhere to what a black hole actually is, and to what extent does mathematical modeling even figure in something like, say, TV shows or books or what have you? If you could, please.
Well, the thing that comes most to mind with like black holes being portrayed falsely in science fiction is, anyone see the movie Interstellar with Matthew McConaughey a few years back?
I remember it, yes.
A black hole and like travels through time and stuff. You know, that was pretty out there, because even if they could send you through time, which I guess, since gravity has an effect on time, theoretically it could send particles through time. The fact is your body would just be stretched out into a million pieces because of the difference between the gravitational force between your feet and your head as you're falling toward the black hole.
Wow. Okay.
And astronomers actually have a word for that. It's called spaghettification, because you just get stretched really far because there's such different gravity on your feet and your head that it pulls you apart.
And this may be a stupid question, but is the theory that you don't survive this, or do you I guess no one really knows, but my assumption is with spaghettification, you don't survive.
Yeah, I mean, I'm no expert on anatomy and physiology, but I feel like if you're stretched far enough, your organs are going to be destroyed and your bones are going to break. It's not going to be a fun experience.
Right. So it doesn't alter your well, I guess we don't alter the laws of physics by it when that happens. It just
Right.
Okay. All right. Splendid. Thank you very much.
Sure.
Well, my next question, I don't see any hands, so Maeve, I'd like to ask a question of you. How did you choose the 3 concert halls that you used in your study? And that's part 1 of the question. And part 2 is, you mentioned at the end that we're taking greater care now when we restore buildings like this to look at the acoustic function and how it can be improved. Is there also an effort, rather than improving it to our modern taste, but returning it to what it might have been originally? And is there a disconnect between the two?
Yeah, so I chose the 3 different concert halls because they span the range of reverberation time usually found in concert halls. The lowest reverberation time you're probably going to see is around 1.2 seconds. And those are actually usually opera houses because they have a very crisp sound, which is good for understanding speech and singing, but they're not as great for instrumental music because you don't have that rich blending sound. Whereas on the other hand, with the 2.0 seconds, some concert halls go as high as 2.1 or 2.2. But if you get any higher than that, then it just kind of sounds muddy, even in music. And so those aren't very good for speaking or singing at all. So one thing that I actually have looked at before with kind of historical architectural acoustics is that different concert halls have different purposes. So like I said, opera houses usually have lower reverberation times, whereas concert halls usually have higher reverberation times. But if you notice a trend throughout history, concert halls the reverberation time became higher and higher because of advances in instrumentation and in how music was being presented. So it is really important. There are people trying to restore things to their previous sound, how they sounded historically, because it's used to portray that historic music. And there's concert halls that, even though they were built historically, we have been trying to change them to be different from their historical acoustics. So prime example of this is the Royal Albert Hall in London, because when it first opened, it had the volume was so large that the reverberation time was around 2.8, 3.0 seconds, which is just too long for you to really understand and appreciate anything that's going on in it. And another thing with this hall, it has a lot of echoes. Like you could distinctly hear a different echo, whereas reverberation time isn't echoes, it's just sound energy that hasn't yet died out. And so this is a concert hall where people have been trying to make it closer to a reverberation time that's acceptable for most music.
Okay, thank you. Just as a follow-up question, I can see how your research would have applicability for instance, restoring instruments like violins and cellos and so forth. My other question is, how does digital music or the playing of digital music intersect with your work, and does it? Well, I guess first question is, does it? And secondly, is there I guess there is a quantifiable difference between digital music in these kinds of venues and what we would consider to be more traditional?
Yes, so this is something that I'm really interested in, and I haven't been able to research a lot, but I do know that as the digital age has progressed and we have more recording technology, and as microphones have gotten better and speakers have gotten better, that really has had an impact on music. Especially if you go into a recording studio, those are very quiet spaces, usually with a low reverberation time, because instead of using a space to create reverberation, we're kind of doing what I did here, where we're artificially adding reverberation into the music. So that is something that I think is really interesting, and I'd love to try and understand how recording technology has changed how we experience architectural acoustics.
Is there something like a deep fake in audio technology that we've heard about in video technology? I mean, if I were to play a Stradivarius and then recreate it digitally, would you be able to tell the difference?
Usually you can. So this is something, when synthesizers first became widely used, they weren't actually digital reproductions of, say, a piano. If you played a synthesizer and you wanted it to sound like a piano, it was an actual recording of a piano. They recorded how the note sounded on a piano. And so that, even though it's technically more realistic because it's actually a piano, it sounds fake. It doesn't sound realistic. So yes, you can tell the difference between a Stradivarius and a digital reproduction of a Stradivarius, but only if you're listening to that violin in person. It would be really hard to tell if you're listening to a recording of it.
All right. Thank you very much. Thank you.
You're welcome.
I don't want to monopolize the questions. I do have one for Michael, but I wanted to make sure that if there was anyone else who wanted to ask a question at this moment, that you had an opportunity.
I have a question. If that's okay.
Please go ahead.
I'm still trying to think about it, but I'm just going to throw it out there, and that's for Cole. So we really kind of talked about a basic of calculus that you mentioned, and talking about there's basic things you mentioned that we should have known from calculus, even a little bit of pre-calculus into calculus. One thing as simple I kind of want to mention is, how do you account for doing basic addition subtraction with infinity? Obviously we know there's uncountable and countable values. So if you were to do, for example, an infinity that's uncountable and subtract that from an infinity that's countable, how can we come up with a conclusion of infinity as an answer? Would that be considered countable, or is that still an uncountable number? I can type in the chat if that was too much, but
no, I understand what you're saying. That's a really good question. So for if you subtract, for example, you say 4 infinity minus 3 infinity, you're still going to get infinity. You get 5 infinity minus 3 infinity, that's still going to be infinity. Now, so if we're going to an uncountable form of infinity, no matter what you add or subtract, that's still going to be uncountable, even if you're adding a countable infinity. Because remember, we had the list of all irrational numbers. That was an example of uncountable infinity. And if we include the rational numbers, then that's still uncountable infinity. But you take the rational numbers away, so you subtract aleph null, you still have uncountable infinity, if that makes sense.
that's perfect. Thank you.
Mm-hmm.
Okay, well, may I ask you a question, Michael?
Sure.
Oh, about the idea of the modeling. Can you, you listed a few examples of how it can be used. Is there one in particular that you found most interesting, and why?
I think in terms of applications, I think university admissions is very good, and using the modeling of just the general matrix structure is very important for these applications. Just because when we model parallel algorithms, we kind of want a way to visualize how the processing elements are set up. So you can actually just visualize that we have one processing element or one computing node per matrix entry. So it makes it very easy to translate algorithms and see how they communicate, as they usually communicate next to each other, or you can do it across rows, across columns. And I think that's the main benefit of the PII algorithm in terms of these applications, because normally when we parallelize traditional algorithms using like array structures or listed like preference lists. This matrix-like structure is not possible, and it's not easy to parallelize algorithms without this kind of modeled structure.
Now, are you saying that these algorithms are removing bias?
I think that's hard to say in terms of especially stable marriage when a lot of the matching, like the gender optimality I mentioned, was you have male preferred and female preferred or female optimal matching sets. I think there's a big hit towards in evolutionary algorithms towards maintaining diversity. As you'll see, what we consider like a Pareto optimal solution in like stable matching would follow, since there's not one stable matching per input, there's multiple. We can model those on a curve, and there's a lot of work in maintaining that diversity along the curve instead of converging to a few what are considered optimal matchings. And I think that's a big step in machine learning that's being researched. But would I say that these algorithms preserve diversity? Not necessarily. I think the work in gender optimality pushes towards a need towards preserving the optimality diversity in input sets.
Okay, wow. All right, thank you. I have a question here in the chat. This one's for you, Maeve. In relation to the first presentation, I guess Cole's presentation, can you discuss the line between theoretical and applied studies, and do you usually lean toward the second, and why?
So, to me, theoretical studies look at how something could be. In acoustics, there aren't usually very many theoretical studies because it's a physical phenomenon. And yes, we can use mathematical models to help us predict what would happen, but that doesn't necessarily mean that's what's actually happening. So the software that I was specifically using, although it's a mathematical based software, it has a finite limit. I was sending out what's called rays, so just lines of sound, basically, from my sources. And then they were bouncing off of the surfaces based off of the material properties of the surface. And I had a finite number of rays that I can produce before my model would just crash because it can't compute that many. So although that can help us get a really good idea of what's happening in the space, the only way to really make sure that what is actually happening is true is to go to those physical spaces. And I wish I could have visited them. I have been to the Kennedy Center multiple times, but I never brought any equipment with me to try and listen to the reverberation time or anything. So I think applied studies are more useful, especially in acoustics, but theoretical studies, similar to what I was doing, can help us figure out what's going on so that we can look more closely at one specific aspect of these applied studies.
All right, thank you very much. We have another question in the chat. This is from Matthew McDonald, and it's from Michael. What was the constraint on the high performance computing system you mentioned that only allowed you to model a set size of 20?
Yeah, so the main constraint was that the PII algorithms, they use n-squared processing elements. So using 20 or n of 20 would allow for 400 nodes. And the cluster at Salisbury University does a max of 424. We tried oversubscribing on the cluster, but this led to exponential increase in time complexity, so we didn't include those results. But as a future work, we do want to test on a larger cluster to test larger set sizes.
Right. Just so I understand, does that mean you're using a larger computer or several?
Several, but several. A larger group of several.
A larger group of several, both. Okay. All right, great. Thank you. All right. Any other questions? We have a few minutes left. Well, looks like I
really don't have any. Sorry.
Oh, no. Go right ahead, Justin.
I really don't have any more questions. Everyone did like a really good job here, so I'm really impressed.
I think I see Don had a question for me. If there's time for me to answer it.
Oh yes, we have time, of course.
Okay. Don asked, how was I originally drawn to this topic? And what related topics might I go next? So I actually saw a video about infinity when I was taking Calc 3 that semester, and I was trying to think of a topic for an honors project, and I saw a video about infinity, and I just thought it was so cool. I had to do my project on that. And yeah, so this was actually my project for the spring of 2020. So fall of 2020, I did a relation of linear algebra to economics and how we could apply that to learn more. And now this time around, I'm taking a statistics with probability class, and I'm doing a honors project about how some advanced statistics measures are being taken to enhance the world of sports professionally.
By that you mean how players are chosen and trained, or how do you mean?
Both with that and with making decisions like play calling, like for example in football, how we see it used to be if it's 4th down you always punt, but now they use the analytics and probability to figure out whether punting is the right decision or going for it. And so I'm just going to be laying out some of the mathematical methods they use and how these decisions are figured out, both with players and play calling.
Okay, well, that's a very interesting question, because if this is happening in the coaching world, are we shifting from, say, coaches who coach from, for the lack of a better word, who coach from the gut and from their experience, to more statisticians?
Yeah, I think the statistician group is definitely taking over, like the Houston Astros, and obviously their reputation has changed a little bit with recent events, but their manager AJ Hinch was a math guy. He never played or anything. He was a math guy who got hired to make decisions based on the numbers, and of course he also cheated, but that's a separate issue.
Yeah, human nature corrupting the math.
Definitely.
I suppose. So yeah, again, you may have seen this book Moneyball, about how mathematics is taking a larger role in, at least in baseball, certainly, which is of course a game of statistics. But
yeah, that's a big part of my project that I'm working on this time.
oh, wow, you must be very excited that we have a season again.
Yeah.
more chances for data.
Yeah, that's great. Last year was just a fluke.
It was. Well, we have just a few more minutes if there are any other questions. Well, if not, just let me say that as a non-mathematician, although I'm from a family of mathematicians, thank you all for very interesting presentations that you worked very hard, I could tell, to make them understandable to a large audience. And so I appreciate that. And I think we all got quite a bit out of your work. And I'm looking forward to seeing where you push these topics, because each of you certainly have, the tools here to really make some advancements and strides in mathematical modeling. And thank you for bringing it to us today.
Thank you for the opportunity.
And thank you very much.
You're quite welcome. And we look forward to seeing you in 2022, when in NRHC, we hope we'll be having an in-person conference in the city of Philadelphia. So we look forward to seeing you there.
Sweet.
And again, splendid work, splendid work. Oh, actually, just let me take one last screenshot of the three of you for our website. And thank you very much. It was a pleasure.
Thank you.
Thank you.
Thank you.